think the fan might be a little bit overkill. This is part 2 of the video series on making the custom 3D printer heated enclosure. And before we jump into the video, I've noticed that a lot of people who are watching these videos aren't subscribed. If you like these videos and you like what I'm trying to do here, please subscribe. It helps a lot. It helps get the videos out there. And same with liking the videos, that really helps a lot. So where we left off was basically just laying out the ribbon cable and the heaters and the exhaust fan. One thing that I did change, and I think the only thing that was changed in this from last time, is the fan that I have has a 24 volt version with the exact same specs. So that makes it so we don't need a separate, pretty efficient regulator to drop that down to 12. So that definitely makes more sense than the 12 volt. Other than that, it should be basically the same. So from here, typically the next thing I'll do is start working on the power supply side. So coming in from the board, and I always started on the top left, will be a 2-pin power connector. And for this, I'll just use a generic connector from the KiCad libraries again. And then label that PN. And there's a lot of different ways you can do input filtering. I'm not the greatest at deciding on how to do that. One of my other engineers is really good with that, but I'll just kind of do kind of a generic filter, which we'll do the majority of the times. So we will start with just a generic fuse because we don't know the power calculations yet, and then go straight to a TVS diode, which we want a 24 volts. That means it has a reverse standoff voltage of 24 volts, and it will fully break down at a maximum of 38.9 volts. So what's really nice about doing a TVS diode like this, now we know that anything downstream of this is guaranteed to never be above 39 volts, even on a transient. So that's one of the reasons I really like having those there. Next, I will add a electrolytic cap at 50 volts. Again, as long as it's over, say, 40 volts, you know it's going to be safe with that TVS diode. And then a 0.1 ceramic. And essentially, when you stack different values of caps, both electrolytic and ceramic, what it does is allows you to have different transient responses at different frequencies. Again, I'm not an expert in power filtering. That's kind of that, and EMC is kind of a study all of its own. But this is kind of a good ballpark for most applications. Nothing on here is really high frequency or noisy, and we're only going to have probably one switching power supply. So it shouldn't be a big deal either way, so I'm not overly concerned with it. So then we'll add our 24 volt supply, and then our ground here, and then actually let's do one more electrolytic cap. I like having a bigger cap also, just to help with real low frequencies and as kind of an energy store, since we're going to have some pretty high powered stuff down the line. Now we will add both of our power flags to keep KiCad happy, and I like making both those invisible. Alright, so that is our main input filter. So now from here, there's a few different routes we can go. Since we already have these two heaters drawn, I guess let's do the driving circuitry for them. So I have a few that I like to use. NCP. So the one that I want to use for this is an NCP 81070, 81071. And I've used this one a lot. What's nice about it is it has two separate outputs from the same chip, which makes it really easy for driving stuff like this. And then for the MOSFET, let's go with one of the IRFs. We should be able to get away with this one, which is only in a D pack. That's a D squared pack, so this is pretty small comparatively. And if I've gone into pretty good detail on choosing MOSFETs in the past, so I'm not going to go too in depth here for the sake of time. And when you use a MOSFET driver, you typically don't have to use a gate resistor, but it's still always kind of a good idea. As long as you're not switching it at high speed, you don't really have to worry about the value. And all this does is you have to remember that when you initially turn on one of these FETs, the driving circuit sees it as a dead short. So depending on what is done internal to here, you can overload one of these. So having this 100 ohm resistor just kind of dampens that initial inrush. And since these are resistor heaters, we're not going to be using even remotely a high value of PWM, so that's not going to matter. High frequency of PWM, that is. So we have our two FETs here. Now let's grab the ground labels here, like that. And for the INAs, IN A and B, and EN A and B, the INs are what are actually controlled with PWM, and then the enable channels just basically say if they're active or not. So I will just tie these to your input voltage, and then these are what are actually being controlled. So I will do that now. And for these, since like I said, they initially see it as a dead short, I always throw on two decoupling caps here, usually a 0.1 and a 4.7 microfarad. And now the one really annoying thing with picking these gate drivers and the MOSFETs, very rarely can you find one that will be able to work with like a 24 volt supply. So I just know this from using these in the past. You want to have about a 12 volt supply here, and they don't use a lot of current. So we can just grab a 12 volt supply just from a linear regulator. It doesn't have to be a switcher or anything. So what we can do now is take care of the linear regulator for this. And this, I'm just going to use a standard LM317. I'm, again, not going to go into detail on how I set this up. These are like the most generic linear regulators there are. Okay, so here is this linear regulator done. And based on the calculations of the adjusting resistors, the output voltage is 13.75 and not exactly 12. For this, all you need is 10 volts to make sure that these FETs are completely on. So it doesn't have to be exactly 12 volts. I just use that label because it's convenient. So now we can bring this back down, and I can already tell we're running out of space. So let's go to the next size up in the paper and move these over. Okay, so the next thing that we are going to do is add the 5 volt supply, and that should just be a 5 volt power flag. We're going to do the 5 volt supply for the ribbon connector and then some other circuitry on here that requires it. So let's move this down. And for this, since the touch screen draws up to like 200 milliamps and some other stuff might get up to like 300 or 400, That's definitely going to be way too much for a linear regulator coming from 12 volts. So we will need a switcher. And I'm not going to go into too much depth on the circuit design of this switcher. For the majority of the time, what honestly is usually the easiest thing to do is use a TI chip and use their simulator online. It is really good for the majority of use cases. As long as you only have one switcher on a board, that really will do a great job of choosing your input and output caps and your inductor. So that's what I did for this, and I'm just going to go through with the values that I got from their simulator and throw this together. Okay, so that is the regulator done, and of course we have to add our output 5 volt, our output 5 volts, and again a power flag to keep KiCad happy. And this is a pretty straightforward switcher. There's really nothing particularly interesting with it, other than you have to check on the pinout sometimes. Typically with an enable pin, if you want it to always be on, you would pull it high. But for this chip, for whatever reason, to make it high, you keep it floating. And since we're never going to be turning it on or off, that's how we want to keep it. So that's just something to keep in mind with it. And now the next thing we can do is do the PWM signal. And even though it is a 24 volt fan, the PWM line is 0 to 5 volts. And unfortunately, even though our ribbon cable takes in 5 volts, it has an internal 3v3 regulator. So everything on here is logic 3v3. So we can't directly switch that PWM line, but that's not a big deal. I'll show you a pretty easy way, just using a standard signal FET that you can switch a different logic level pretty easily. So connect this here to ground, and our fan PWM line goes on the high side with our 5 volt line on that. And then for this one, we need to have another PWM line so that we can use PA6 for. Change that to input, and again we'll add a little gate resistor here. So when this is low, there's nothing flowing here. This stays at 5 volts. When this turns on, this is a dead short. Forgot my resistor. Yeah, that would not be good. So for this, resistor value really doesn't matter much. Let's take a common resistor that we have here and tie it to here, and then move our PWM line on the bottom side. So when this is low, there's no current flowing here. This all floats up to 5 volts. When this drops down and when this turns on, this goes to ground. This side is ground. The 5 volts is dumped across this 3K3 resistor, which will be a little over a milliamp, so we're not burning much off. Okay, so now the next thing that we can tackle are the LEDs on here. And just because I have used these in the past, I'm going to go with these pretty high-powered diodes. They have a thermal pad, which is really nice, so the heat gets dissipated to a neutral pad, which you just tie to ground. And they work really well, and they're super bright. So most likely we will need to dim these down. And for driving LEDs, typically the most efficient way to drive them is with a switching constant current supply. But for this board, generating heat actually isn't bad because we're going to be heating the enclosure anyway. So for the sake of not adding any extra complexity, I think the best bet is just to drive these linearly. And I did this calculation earlier, so let me just copy it over. So if we're driving it linearly from a 24 volt supply, the forward voltage of these LEDs are 2.7 volts. If we throw 8 of them in a strand, that means we have 2.4 volts to drop on that entire strand. So that's what extra power or extra voltage needs to be dissipated. Since it's linearly driven, it'll be dissipated through a resistor as heat. And for this, what we are going to go with is assuming that we will drive these at a maximum current no more than an amp. If we use a set of 1.8 ohm resistors, that gives us a maximum current of 0.67 amps, and that means that we will dissipate 2.4 times 0.67 amps, a total of 1.6 watts across those two resistors. And that we can just place here. So we will go with 8 LEDs. Eight LEDs like that. And now let's grab our resistors. And these are 2-watt resistors, so we have a total of 1.6 watts. That means since these are symmetrical, both are 1.8 ohms. Each one of them will be dissipating 0.8 watts, so we're well under 50%, which even with thermal derating, we should be plenty good there. Again, 0.67 amps, these are going to be way too bright for what we need, so we're going to be PWing them a lot lower. So that's just the absolute max that we will drive them at. So we will take the 24 volt supply and take ground right here. And again, these are thermally neutral or electrically neutral thermal pads, so we can tie them to ground, which will have a nice beefy ground plane under here to help dissipate it. Let's use that to ground, and then move this here, and now let's add our driving circuitry. So since we already have this already done, let's just take this exact same circuit, take this here, get rid of this one and this one, and drop that right in its place. Okay, so now the next thing that we can do, someone else suggested this, I don't know if it was YouTube or Reddit, that we might want to have some fans blowing on those resistive heaters just to help kind of circulate air. Okay, so it seems like the battery died on my camera, but that's fine, probably was taking too long anyway. So the only thing that I had done is I put in 3-pin fan connectors, the center one being the fan PWM, with the exact same control over here as was on the other. And then I renamed the exhaust fan to be exhaust, and then the other fans to all just be general fans. They're all tied together because when it's used, they're all going to be circulating the air identically. So now there is really just 2 other things that we need to do, and I'm going to try to get through these kind of quick as well in the sake of time. So the original idea that I had for the to tell if the printer was on was to use like a motion sensor or accelerometer, which probably was a pretty bad idea. So one suggestion was to use a current sensor and tie into one of the extruder heaters. So that's what I think I'm going to do. And instead of us doing a integrated current sensor, we'll probably just use like the Pololu, I think that's how you say it, one of their Allegra breakout boards, because I don't want to have the current path very far. So in order to do that, we can take one of these 3 pins, name it current sense, have the bottom pin be ground, have the top pin have a fuse. Again, anything that leaves the board I like to have be fused, just to protect against, again, a dead short. And then the center one we will label as VIO out and make this an output. So these 2 pins power the current sensor, and then the output line goes to the VIO out, which this will need to be on PAO 0. So actually what we can do instead to keep everything consistent is just name it PAO there, and this should be an input. Okay, so that is our current sensor. Okay, so I just rearranged these to make them a little cleaner. Now the last thing that we need to add is a temperature sensor. And for this, I'm just going to use a I2C sensor that I've used a lot in the past. It's powered by 3v3, and we're also going to need to add a 3v3 regulator after this, but that'll be the last thing we do. And anytime you have an I2C line, you have to have a pull-up resistor. Actually, I was wrong. It's powered by 5 volts, not 3v3. And then the A2, A1, and A0, all that is to change the address. Since we're just using a single one, we can just tie them all to ground. The OS pin, that is just a interrupt pin. The code that I have for this that I've used in the past just pulls it whenever we want. We don't need a real-time update. Move this there, and now just add a 0.1 microfarad decoupler like that, and that is the last main piece of circuitry that we have to add. Okay, so now the last component that needs to be done is we need to have a 3v3 regulator for our current sense driver, which is really annoying that we have to do it just for that, but we'll just use a linear regulator again. So we'll take it from the 12 volt just to help spread the heat around, and then this is 3v3. Okay, so at 220 and 360, that gives us 3.29 volts. Okay, and that is pretty much everything on the schematic. I'm sure there'll be a couple minor changes for the next video when we start the board layout. And please let me know if you have any suggestions or thoughts on this going forward. And let me know if there's anything in here that I went over too quick that you would like expanded on in maybe its own video or a series. And also, let me know if you like these longer format videos. It's just really hard to get all of this in a shorter video. So thank you as always, and I will see you in the next video.